Thanks very much for the invitation. I'm going to give a summary of examples of interactions between sea level and the very high rates of extension and rifting that we have in the Corinth Rift in Greece. The first slide I'm showing here, the map, is showing you the overall rift. It's a relatively small and compact rift. It's very young, it's highly active, as I'll explain. And here we're seeing the entire kind of fault network, including all of the active faults, many of them on the margins of the now marine Gulf of Corinth, and some of them within the rift. So a thank you to all my colleagues who I'm using contributions from many of them. So just a bit of an overview of the sorts of things I want to cover, an introduction. So first of all, the Corinth Rift has some of the highest rates of extension of any rift. And therefore, we have a real scope for high resolution of processes going on there. So rates of extension are up to 10 to 20 millimeters a year. We've got uplift rates of several millimeters a year, and similarly for subsidence. Fault slip rates up to 8 to 10 millimeters a year in some cases. And the sediment accumulation rates in the basin are up to 3 to 5 millimeters a year. So high rates and high resolution. The basin, as you can see, is at sea level today. So we have got this really strong interaction with changing eustatic sea level. So that means we've got a wealth of uplifted high stand terraces, low stand submerged terraces as well. And then we're also able to see stratigraphic changes that are reflecting the changing environmental conditions in the Gulf over time as sea level changes. So it fluctuates between marine and a more sort of lacustrine kind of environment. We've got great data coverage. And I presented in this series before to show you some of the examples of those. So we've got a really dense network of seismic reflection data offshore. We now have IODP, scientific ocean drilling boreholes as well. And onshore terraces have been really quite thoroughly mapped as well. So we can use those sea level rift interactions to quantify rates of fault network and rift development. And I'll explain a bit how we do that. We can calculate fault slip rates and therefore help with hazard assessment. And we can also resolve details of the paleo environment and the impact on fauna for a semi-connected basin through time. And potentially we can also make contributions actually to the detail of global as a eustatic sea level change, which is maybe unexpected. So the rift, as you can see in the top right map, is marine, or the Gulf is marine today, but we have a number of sills and connection points with the open Mediterranean. So in the west, we have the Rion and Aculos Cape Papas sill, which are around minus 50 to 60 meters. And those are kind of the connection points in the more recent past. And further back in time, we have the Corinth Isthmus, where the Corinth Canal is, and this has been a connection point in the eastern side as well. So we've got these basin bounding sills, and they're creating this semi-isolated basin during late Quaternary low stands, where the basin is basically detached from the Mediterranean. So there's always long been this hypothesis that we've got alternating marine and lacustrine basin environments, and people started to tie the seismic stratigraphy, as I'll show you, based on that inference. And now we have borehole drilling, we can kind of confirm that correlation. We can use it to kind of estimate and confirm ages as well as the environmental change. And then the rift-related deformation is also creating uplifted marine terrace sequences and submerged subsided terraces as well. So you can see in the bottom right some details here. Just get the pointer. Oh, sorry. I'll try and get the pointer going. Hold on 2 seconds. Yeah. So we can see here also some details of those sills from a paper by Spiros Sergiu, published quite recently. So you can see their depths. One of the issues you might be thinking is, do we know that those sill depths have remained constant with time? And that's a good question. And the answer is no. And in fact, I think the drilling data helps us to resolve that question. So I'll just sort of go through some of those different elements of sea level interaction. So if we look on shore, I mentioned that there's a number of uplifted marine terrace sequences, particularly on the southern margin of the rift, so along the southern shore. So this is where the southern border fault system has developed. It's got the highest slip rates and therefore the highest uplift rates. And so we've got a number of locations where terraces are preserved here, including the fairly famous sequence of Corinth terraces around here, near the town of Corinth. And so you can see an element of those on the left. And this is actually using much more modern satellite data now that Gino de Gelder put together. And this is the sequence of terraces that have been resolved there in the past by Rolando Armijo and others. So here and elsewhere, where these dots that you can see are all representing where marine terraces have been uplifted and either independently dated or a mixture of dating and then sort of correlation with the sea level curve, we've been able to get uplift rates for a number of faults, which you can see on this plot, which comes from a paper by Casey Nixon that was published recently. So we've got a lot of this information, particularly on the southern shore of the rift. So the ages of those terraces are going back as far as stage 9, which is sort of about 350,000 years old. And as you can imagine, with the high rates of uplift, we've got quite a lot of detail in terms of individual parts of those stages. And the uplift rates, as I said before, are of the order of sort of 1 to 1.5 millimeters a year over the sort of that time period. And then offshore, we can also use those sea level interactions for two purposes. One of them is just being able to use the seismic stratigraphy to resolve or pick out those marine and lacustrine sequences. So early on, people looked at seismic reflection data and noticed there were amplitude differences, and you'd got this sort of cyclicity in the Corinth Rift sediments, and that was interpreted as representing marine and lacustrine periods. And people made correlations with the sea level curve and therefore a rough initial interpretation of age. And now with drilling and with other shallow cores, we've been able to confirm that that is indeed the case. So now we've got more robust ages to assign to that seismic stratigraphy. But in addition, there were some details that you could see, and this is a paper from Becky Bell some time back. And here, what we're actually looking at is some of the low stand sort of deltaic cliniforms that you can see in detail here. So these are, again, something we can use to determine rates of subsidence and see the details of that sea level interaction. That, of course, requires a bit more knowledge about the sill depth and therefore what the level of the basin was. But again, it's been used to kind of quantify rates of subsidence and therefore extension overall. So as I said before, we've also recently had scientific drilling here. So this was in 2017. We drilled a series of boreholes, and I'm just showing you results from one of them here in the center of the Gulf of Corinth. And here I'm focusing on the upper unit. So this is the one where we've got this fluctuation between marine and lacustrine environments. And sure enough, we found that there was a distinctive lithology in the marine intervals, and then in the isolated or lacustrine intervals. So quite different lithologies, heavily bioturbated sediments in the marine ones, indicating a lot of faunal activity, whereas in the isolated ones, we found more preserved bedding and laminated sequences. And interestingly, between them, we had quite interesting transitional sequences that you can see here, very highly laminated and sometimes including aragonitic varves as well. So quite a nice sequence, and you can see that the blue is representing marine and green is those lacustrine intervals. As we get further back in time, we have less and less marine, and that probably is reflecting the position of the sill back through time. And quite distinctive microfossils, which you can see here as well. So we had sort of more marine forams in the marine sections, and then some interesting stressed diatoms in the lacustrine sections. So we've been able to correlate the stratigraphy in those different intervals between the 3 boreholes we have. This is just showing 2 of the boreholes. So again, you can see the blue representing that kind of more marine sequence, but not only seeing marine and lacustrine here, but also some of the details of the different lithologies that are being generated. So different sedimentary environments that are really, really, really clear in their differences as we go back through time and change this paleo environment. So we can use this information because we've taken it to confirm the ages of different stratigraphic horizons within particularly the offshore Corinth Rift sequence. And so from that, you can actually get a lot of detail about how the rift is evolving itself, how the faults individually are evolving, the rates of their motion, how the southern border fault system has evolved and linked together. And so these are some results from Casey Nixon's paper this year, which integrated the drilling data with the seismic interpretations that we'd already made. And you can see some detail on the left here of over quite short time intervals of sort of 100,000 years or so, how we're seeing slip rates on individual faults changing and increasing, and how they're linking together to form this southern border fault system. So that overall, the extension rates and deformation rates are increasing, and we're seeing these individual faults linking together. So a really nice sort of detailed picture of how the rift has evolved in high resolution. And he also has some very nice cartoons that show how that rift structure has evolved, and sort of acceleration of rates of deformation that we're seeing in the last 300,000 years. And so this would not be possible really without this sea level interaction giving us, the sort of the timeline as we go through the sequence offshore.
That's just over 10 minutes, Lisa. Thanks.
Okay, thanks. Just a couple more slides. So just a little bit more back on the sort of other things that we learn from this sea level interaction. And this is just a series of slides that should show you how the environment has changed, or a sort of a proposition of the model of how it's changed from a marine basin where we've got overturning and mixing within the basin and oxygenated bottom waters, as you might expect in a kind of open marine basin. And we've got sort of a diverse faunal assemblage. But then that switches when we go to a sort of more freshwater lake. It's not fully freshwater, but we've got stratification, oxygen depleted bottom waters, and that's causing a stressed seafloor environment. So we see a completely different range of microfossils. And there's other things obviously going on climatically in terms of evaporation and sediment input and precipitation. So a really nice sort of model showing those differences. And then some sort of suggestion of how that might look as you transition, as water starts to go over the sill and you start to have that influx of marine water into the basin, and how things start to change. So some quite nice sort of schematics that just sort of show what we've learned from the drilling. And then my final slide is just something that we weren't necessarily expecting, but because we've got these really high resolved details because of the very high rates and high sedimentation rates. This was a study done by Ilaria Mazzini and Tom Cronin looking at ostracod taxa. And they were actually looking in a lot of detail in the last 20,000 years, looking at how the marine and non-marine taxa change through time in detail. And what they're seeing is that as sea level rise occurs over that time period, particularly in this sort of 15 to 10,000 year time period, they're seeing a really sharp change in the non-marine taxa decreasing and the marine taxa increasing just around this time when we have globally an acceleration in sea level rise. So they're really picking this up, and therefore the scope to potentially actually resolve maybe unknown details of eustatic change in some of these very high rate moving rift basins. So I'll stop there. Hopefully that gives a bit of a summary.
Thanks very much, Lisa. Excellent. So I'll open the floor up to questions. If you just raise your hand, then I can see it in the list of participants. Any questions? Any in the chat? Yeah, let's have a look. Okay, well, I'll ask a question then. So Lisa, you mentioned that you could date these terraces on the footwall to about 350,000 years ago. Is that saying anything? Is that just because of preservation of these features?
That's a good question, and I should sort of add a little bit on the sort of data techniques that people have used. It is based on corals, and obviously they're not everywhere. So you kind of have a few sort of marker points which give you a sort of an absolute age, or reasonable age, and then we obviously have some radiocarbon ages for younger things. Yeah, that's a good question, and it probably is mostly about preservation, although as in the older ones are not preserved. But as you might have seen, as we go back in time in the drilling data, we do start to find that the marine intervals are rarer and thinner in the Gulf, presumably because the sills that are making that connection have gradually been subsiding. So they've been at higher levels in the past, and therefore we might be actually seeing some cutoff in sort of lengthy marine periods in the basin, and therefore not having the ability to generate those terraces. So we could be seeing that, although I'd say 300, 400,000 years is a bit recent, but yeah, so it's probably a combination of those two things.
So you mentioned this sort of increase in, I don't know, deformation rate about 300,000 years ago. Is that increase in extension rate or faulting
Yeah.
rate?
Yeah, so it looks like if you put together sort of cumulative slip rates on the faults across the rift, which is what Casey did, and look at that through time, it increases, and there's quite an acceleration around that sort of 300 or so thousand years ago time period.
Is
Yeah.
there an explanation for that? Any?
Well, people have talked about sort of, well, I think that the linkage of the southern border fault system is probably doing that. So actually, that process is causing some acceleration, and people talk about sort of ideas of sort of rift climax and sort of some acceleration occurring. But in terms of exactly what role those might play and sort of deeper structure, deeper processes, I'm not sure. But I think some of it is certainly to do with that linkage of the main border fault system.